In this section, we're going to study the simplex method for maximization problems with problem constraints that are of the form less than or equal a non-negative value. These are called standard maximization problems. Example 1, we're going to maximize p equals 50x1 plus 80x2 subject to the constraints x1 plus 2x2 less than or equal to 32, 3x1 plus 4x2 less than or equal to 84, and x1 and x2 are non-negative. Step 1 is to set up the initial system by adding slack variables and rewriting the objective function p. In the simplex method, we're going to put these constraints and objective function into a matrix, and so we need equality. So we add variables that will take up the slack or help us gain equality in the constraints. So our initial system is x1 plus 2x2 plus s1 equals 32. Now s1 can be any number that creates that equality. In our second constraint, we're going to add s2 as the slack variable. So we have 3x1 plus 4x2 plus s2 equals 84. Now notice, we rewrite the objective function p. We want to keep p positive, but we want our equation to be equal to 0. So we're going to move our x1 and x2 terms to the left. So we have negative 50x1 minus 80x2 plus p equals 0. And x1, x2, s1, and s2 are all greater than or equal to 0. The next step is to set up the initial simplex tableau and to identify the basic and non-basic variables. Remember, the basic variables are non-zero, and when we see them in matrix form, they're usually going to form a basis or the identity matrix. In the initial tableau, the slack variables are usually the basic variables, and p, or whatever you're labeling your objective function to be, is always going to be considered a basic variable. The procedure for selecting basic and non-basic variables is as the following. First, we determine the number of variables, and those do not change during the process. So if you start with 2 basic variables, you will end with 2 basic variables. To select the basic variables, we look for columns in the tableau that have exactly one non-zero element. Now, that element is usually the number 1, but it doesn't have to be. Another stipulation is that the non-zero element cannot be in the same row as the non-zero element in the column of another basic variable. Now, this procedure will always select p as a basic variable because the p column will never change during the simplex process. Once the basic variables are selected, every other variable is considered non-basic, which means that it has a 0 value in that tableau. So recall our initial system. Our initial tableau, we write our x's in order, so x1, x2, our s's in order, s1, s2, and then we have a column for our objective function, and then our last column is our constant column. And so we're going to have a row for each constraint, and the last row, which we're going to separate by a horizontal line, is going to be reserved for the objective function. So notice row 1 uses the coefficients of our first constraint. So we have 1, 2, 1, 0, 0, 32. This is because our constraint was 1x1 plus 2x2 plus 1s1. There are no s2s, no p's in that constraint, so those get 0, and we're equal to 32. Row 2, we use the coefficients of the second constraint. So 3 in the x1 column, 4 in the x2. There are no S1s, so we have 0, 1 in the S2 column, 0 in the P column, and it's equal to 84. So 84 is in the last column. And our objective function goes in the last row. So negative 50, negative 80. There are no slack variables in the objective function, so we have 0 and 0 for the S1 and S2 column, and we have a 1 P, and that is equal to 0. So now we want to label our basic variables. So we look at this and we say, okay, if we look at the x1 column, I see that I have 3 non-zero values. So that is not what I am looking for. Same for x2. When I move to the S1 column, however, I see that I have 1, 0, 0. So that is a column that has mostly zeros with one non-zero element. S2, I have 0, 1, 0. Again, mostly zeros, one non-zero element. And the P column, 0, 0, 1. So our basic variables are S1, S2, and P. So the way we interpret this is since S1 is 1, 0, 0, the 1 is in the first column. So that means that S1 represents row 1. In S2 column, we have 0, 1, 0. So the 1 is in row 2. So that means that S2 represents row 2. 0, 0, 1 is our P column. The 1 is in the last row, so P represents the last row. So the way we interpret this is that S1 would be equal to 32, S2 would be equal to 84, P would be equal to 0. And since x1 and x2 are non-basic, they are also 0. So now, what we want to do is we want to swap the non-basic variables, x1, x2, and so on, for one of the basic variables, not p, as a step toward maximizing the objective function. So we're going to have to use a pivot operation. So to do this, we first select the pivot element, and we do that by selecting a pivot column and a pivot row. So we're going to locate the most negative value in the bottom row of the Tableau to the left of the P column. The column containing that element is the pivot column. Now, sometimes you may have a tie for the most negative value. In that case, choose either column you want to. The variable corresponding to the pivot column we call the entering variable. Now, to find the pivot row, we're going to divide each positive element in the pivot column above the line into the corresponding element in the last column. The pivot row is the row corresponding to the smallest quotient we calculated. If there's a tie for the smallest quotient, choose either row you want. If the pivot column above the line has no positive elements, that means there is no optimal solution and we stop immediately. The variable corresponding to the pivot row is called the exiting variable. Now the element at the intersection of the pivot column and pivot row is the pivot or the pivot element. We're going to use row operations to change the pivot element to a 1, and we're going to get zeros in the rest of that column. That's going to change it to a basic variable. And then we just repeat steps 3 and 4 until an optimal solution has been found. So let's get back to our example with this knowledge. So remember, to choose a pivot column, we look for the most negative number in the bottom row to the left of the P column. And in this case, we have negative 50, negative 80, 0, and 0. So negative 80 is the most negative number, or we can think of it as the smallest number. So that makes the x2 column, which I circled here, the pivot column. So we call x2 the entering variable. So after I do my operations, x2 should enter the basis. It should become a basic variable. So now we're going to choose the pivot row. So we look in the pivot column and we see that we have a 2 and a 4 above the line. So both of those rows are eligible. So now we're going to take the number in the last row and divide it by the number in the pivot column and see what we get. So notice that we had 32 over 2, which is 16, and 84 over 4, which is 21. So because 16 is the smallest quotient, row 1 is going to be the pivot row. And because S1 was the variable representing row 1, it is now the exiting variable. So it is going to exit the basis. So notice that right now S1 column has the form 1, 0, 0. Well, because x2 is going to switch places with S1, it should look like 1, 0, 0 when we finish. So we want to change that pivot element, that intersection element, which is 2 in this case, to a 1. So we do that using row operations. So we're going to multiply row 1 by 1/2 and replace that with row 1. So our new matrix is 1/2, 1, 1/2, 0, 0, 16 in row 1. Row 2 is 3, 4, 0, 1, 0, 84. And row 3, negative 50, negative 80, 0, 0, 1, 0. So now we've got the 1 in the right spot, but to be a basic variable, you need a 1 and you need zeros everywhere else. So we're going to use row operations to change the remaining numbers in that column to zeros. So to do that, we're going to multiply row 1 by negative 4. That way when we add it to row 2, that 4 will cancel out. And we're going to multiply row 1 by 80, add it to row 3 to cancel the negative 80. And so we get the following tableau. So we have 1/2, 1, 1/2, 0, 0, 16, 1, 0, negative 2, 1, 0, 20. That was our new row 2. And our new row 3 is negative 10, 0, 40, 0, 1, 1,280. So let's label our basic variables. So in the x1 column, we have 3 non-zero elements, so that does not qualify. The x2 column, however, is now in the form 1, 0, 0. So that is the format of a basic variable. And because the 1 is in the first row, x2 represents row 1. Now this makes sense because I was switching x2 with the variable that was in row 1. S1 is now a non-basic variable. S2 and P remain the same, and they're still representing row 2 and row 3 respectively. So now we have to decide, is this optimal? So by our interpretation, x2 is now 16, S2 is still 20, P is 1280, X1 is 0, and S1 is 0. So we want to know if we need another pivot or if we've reached our optimal solution. So if you look at our numbers in the bottom row to the left of P, you'll notice that we do have a negative number, negative 10, that is in the first column. So that means that we have a pivot column, so this is not optimal. So that becomes my pivot column, which makes x1 the entering variable. Now, we choose our pivot row by looking at the quotient of the positive variables in that pivot column divided into the values in the last column. So 16 divided by 1/2 is 32. 20 divided by 1 is 20. So row 2 is our pivot row. So now x1 is the entering variable and s2 is the exiting variable. So if you look at the s2 column, it's 0, 1, 0. That is what x1's column should look like when we finish our row operations. Now notice, in this case, we already have a 1 as our pivot element. So all we have to do is change the 1/2 and the -10 to 0. So we perform our pivot row operations. So we have -1/2 R2 plus R1 to replace R1. 10 R2 plus R3 will replace R3. So our new matrix has row 1, 0, 1, 3/2, -1/2, 0, 6. Row 2 remained the same, 1, 0, -2, 1, 0, 20. And we have a new row 3, 0, 0, 20, 10, 1, 1,480. So let's label our basic variables. So now, in the x1 column, we have 0, 1, 0. So this is a column that has all zeros except for one element. And because the 1 is in the second row, x1 represents the second row. So we write that by row 2. Column 2, the x2 column, 1, 0, 0. That is what a basic variable looks like. So since the 1 is in row 1, x2 represents row 1. Now this shouldn't surprise us because our pivot row was row 2, so row 1 should have remained with the x2. S1 and S2 are non-basic, and P should always be a basic variable. So when we look at the values in the bottom row to the left of P, we see that there are no negative values. So this Tableau is optimal, so we are ready to write our solution. So x1 is equal to 20, x2 is equal to 6, and P is equal to 1,480. Now before we look at an application problem, let's just test our understanding. So consider the following tableau. So we have the columns x1, x2, s1, s2, and P, and our constant column. So row 1, we have 1, 2, 0, 4, 0, 18. Row 2, 0, 4, 1, -2, 0, 21. And row 3 is 0, 2, 0, -4, 1, 24. So let's answer some questions about this tableau. So question 1, which variables are basic? So we are looking for the columns that have all zeros except for one place. So one of the columns that happens in is x1. We have 1, 0, 0. Another column that has all zeros except for one number is s1, 0, 1, 0. And the only other one is P, 0, 0, 1. So those are the basic variables, x1, s1, and P. So all other variables are non-basic. So the answer to B, which variables are non-basic, would be x2 and s2. Now it's important that we know how to interpret the values from our table. So for part C, we're going to find the corresponding values of all of the variables. So x1 we see has 1, 0, 0. So it represents row 1. And row 1 is equal to 18. So that's how we get that x1 is 18. x2 is a non-basic variable, so it is automatically 0. s1 is of the form 0, 1, 0. So because the 1 is in row 2, s1 represents the value in row 2. So s1 is 21. s2 is non-basic, so it is automatically 0. P represents the last row, which is 24. Finally, we want to know if an optimal solution has been found. So first we see if we can find a pivot column. So we see that to the left of P in the bottom row, there is a negative number. So this is not an optimal solution. So that means that either we're going to have to do another pivot or there is no optimal solution. The way we make that decision is we look at the numbers above the line in the pivot column. Since we see that we have a 4 and a negative 2, the negative 2 is not eligible to be a pivot row. But we do see that we have a positive 4, so we could have a pivot row there. So because we have a pivot column and a pivot row, an additional pivot is required. If the 4 had been negative or 0, then this would have been no optimal solution. So let's apply this to a word problem. The Eastern Iron and Steel Company makes nails, bolts, and washers from leftover steel and coats them with zinc. The company has 24 tons of steel and 30 tons of zinc available. The requirements for ingredients in tons per batch and the profit for each product in $1,000 per batch are given in the chart. The company wants to determine how many batches of each product should be produced to maximize profit. So if you see in our chart, we have the nails, bolts, and washers, and we have the corresponding steel, zinc, and profit columns. So the first thing we have to do is we have to label our variables. So we want to ask ourselves, what are we trying to make, sell, or buy? What's our goal here? So the last sentence gives it to us. The company wants to determine how many batches of each product should be produced to maximize profit. So the products are the nails, bolts, and washers. So we're going to let x1 be the batches of nails, x2 be batches of bolts, and x3 be batches of washers. And now that we have labeled our variables, we can now write our objective function and our problem constraints with respect to those. So our objective is to maximize profit. So we're going to write max, we're going to use P, or you could use Z or any other letter that you'd like. We're going to stick with P for this problem. So we're trying to maximize P equals, we see that the nails have 6 profit. So we have 6x1, remember these are in $1,000, plus 2x2 plus 12x3. Now for the steel constraint, the nails require 4, the bolts require 1, and the washers require 3. So we have 4x1 plus x2 plus 3x3. And the company has 24 tons of steel available, so that has to be less than or equal to 24. The zinc constraint, 2x1 plus 6x2 plus 3x3 has to be less than or equal to tons of zinc available, which is 30. And x1, x2, and x3 are all greater than or equal to 0 because we cannot make a negative batch of nails, bolts, or washers. So in order to change this and use the simplex method, we have to first get the initial system. So we need to get equality by adding the slack variables, and we need to rewrite the objective function. So our initial system is 4x1 plus x2 plus 3x3 plus s1 equals 24. 2x1 plus 6x2 plus 3x3 plus s2 equals 30. And the new objective function rewritten looks like negative 6x1 minus 2x2 minus 12x3 plus p equals 0. And all of our x's and all of our s's are greater than or equal to 0. So we are ready to write our initial tableau. So we label the columns x1, x2, x3, s1, s2, p, and then we have our constant column. So row 1 represents the coefficients of the first constraint. So 4, 1, 3, 1, 0, 0, 24. Row 2 represents the second constraint. So 2, 6, 3, 0, 1, 0, 30. Row 3 represents the objective. So we have negative 6, negative 2, negative 12, 0, 0, 1, 0. Now our basic variables we see are x1, x2, and x3 all have all non-zero elements. So those are going to be non-basic variables. S1 is of the form 1, 0, 0. S2 is 0, 1, 0. And the P column is 0, 0, 1. So those are our basic variables. Now, because S1 has a 1 in row 1, S1 is going to represent row 1. Because S2 has a 1 in row 2, it's going to represent row 2, and P represents row 3. So right now, S1 is 24, S2 is 30, and P is 0. And this makes sense because as of this moment, the company has not made any batches of nails, bolts, or washers. So all they have is the full amount of steel and zinc and no profit. So let's choose the pivot column and row. So the most negative number in the bottom to the left of P is negative 12, and that's in column x3. So x3 is the entering variable. So we look at the quotient. Notice that in the x3 column, above the line, we have positive numbers in both rows. So either row is eligible. So now we want to find the smallest quotient. So 24 over 3 is 8. 30 over 3 is 10. So row 1 gave us the smallest quotient, and S1 represents row 1. So it is the exiting variable. So notice that S1 is of the form 1, 0, 0. So that's what we want x3 to look like in just a moment. So that intersection of the pivot column and row, that number 3, we want to change to a 1. So we're going to do that by multiplying row 1 by 1/3. So that gives us a new tableau where row 1 is 4/3, 1/3, 1, 1/3, 0, 0, 8. Row 2 and row 3 are the same for now. So we have a 1 now in the correct position, but we need zeros in all the other spots in that column. So we need to change the 3 and the negative 12 to zeros. So we're going to use row operations. So negative 3 R1 plus R2 will replace R2. 12 R1 plus R3 will replace R3. So row 1 remains the same for this tableau. The new row 2 is negative 2, 5, 0, negative 1, 1, 0, 6. The new row 3 is 10, 2, 0, 4, 0, 1, 96. So let's label our basic variables. x1 and x2 have all non-zero elements, so they do not qualify. x3's column is 1, 0, 0. Because the 1 is in row 1, x3 now represents row 1. S1 has all non-zero elements. It is a non-basic variable. S2 is 0, 1, 0, so S2 represents row 2. P is 0, 0, 1, and that column should never change throughout the process, so P should always represent the last row. So now, is this tableau optimal? Are we finished? So to determine that, we look on the bottom row to the left of the P column, and we notice that we have no negative elements. So there is no pivot column, and that makes this tableau optimal. So let's read out what this says. Since x1 is non-basic, its value is 0. x2 is also non-basic, so its value is 0. x3 is 8. We also know that S1 would be 0, S2 would be 6, and P would be 96. So to maximize their profit, which would be a profit of $96,000, the company should make 8 batches of washers and no batches of nails or bolts.